You can give it a start.
Okay, so hi, I'm Alessandro. Today I'm here to present you the work done by the Linux Feature Working Group in the last few months. It is about the Linux VMA, as you see in the title. So let's start with the agenda. So here's our roadmap for today's journey. We'll start with a short introduction and scope why Linux memory matters at all, especially in safety critical systems. Then we'll look at the VMA architecture, how memory is organized and managed inside Linux. Once we have the landscape, we'll enter into the linear mapping thread, the part where a convenient design turned out in being a safety headache. After that comes the safety feature, defense and detection, what Linux already does to protect itself, and why this is quite not enough. Then we'll move to define the path to functional safety, connecting the dot, what missing, what requirement emerge, and which direction look promising. Finally, an epilogue, wrapping up main ideas, look ahead at what working group needs to do. In short, we'll go from how it works to how it hurts, hopefully without getting lost along the way. All right, let's start with the first topic. Between each session, you'll see a single image like this one. It is not just a decoration. Each picture tells a little story, a different way to look at the Linux architecture. So here we are, the Linux kernel. Picture an old NASA control room in 60. Marvel of engineer, blinking lights everywhere, rows of switches, and very clever people keeping the system efficient, working, and alive. It is beautiful, a bit chaotic, and probably run on caffeine. But look closer, there is a small red light blinking on the panel, the overcommit warning. That light reminds that Linux was never built for safety. It is built for work and to work fast. Convenience, flexibility, those were the original priorities. Safety came much later when people start asking, why do not run this on a car or in a plane? Today's mission is there asking this NASA control room to fly the same rocket, but under functional safety rules. And spoiler, this won't be an easy task. All right, let's open the manual. What this VMA exactly is. Let's take a closer look at the core mechanism, the VMA, the virtual memory area. A VMA is simply a map entry describing contiguous range of virtual memory inside a process, where it starts, where it ends, and what permission applies. Together, they form the each process has many of these, one for code, one for it, and for stack and shared libraries. Together, they form the process virtual private memory. On top of that, a Linux layer, a second map, the kernel's own global region shared across all processes for efficiency. And here is the catch. Unlike the VMA, the user VMA, the kernel region isn't truly isolated. Performance-wise, this is great. It's flexible and fast. From safety point of view, it's far less comfortable. Safety needs hard walls, predictable behavior, and not best effort separation. So the challenge isn't to rewrite Linux, but figuring out how a safe VMA should look like. Something that trades a bit of convenience for deterministic isolation. To get here, we need to ask 3 questions. What risk lie in the current VMA life cycle, what happened under memory pressure, and what are to be changed around VMA to make it truly safe. Now that we know what VMA is, let's see why it matters so much when we talk about safety. The VMA isn't just a bookkeeping tool. It is the main mechanism the kernel uses to manage isolation and resource across different processes. In mixed criticality systems, where one task may be safe and another just doing background work, that isolation becomes the backbone for predictable behavior. The challenge is that Linux doesn't aim for predictability. It aims for flexibility. By default, the kernel uses the heuristic overcommit. It allows more memory to be allocated than physically exists, on the assumption that most processes won't use all of it. It is a clever trick that keeps utilization high, but it adds some uncertainty. You will find out that your memory is not there only when it's needed. Safety-oriented systems prefer the opposite: strict accounting, no limits, and early deterministic behavior for failure. That's exactly what the never overcommit mode that Linux also supports is doing, but very few use it because it limits a lot the flexibility. So somewhere between these two extremes lies a potential compromise: the allocation of usage. The idea is simple: safety critical process pre-allocate everything they ever need, while not critical one keep the same behavior, the default behavior. That way, Linux maintains efficiency for most of the process, while guarantees determinism for where really needs. It is just an idea for now, but it set the tone for what we try to explore, not rewriting Linux, but reshaping it to make it more fit the safety use case. So, where does all this lead? Functional safety has a few non-negotiable requirements: strict temporal and spatial isolation, so one task cannot disturb another; deterministic access to the resources, so timing stays predictable; and protection against unintended interference, whether from a bug, a race, or a misbehaving process. If we translate that into Linux terms, the VMA is right on the center. It defines who holds the memory, how that memory behaves, and what happens when it's under pressure. So when we talk about safe VMA, we are not just talking about a kernel change, but we are talking about an entire ecosystem made by allocators, fault handlers, synchronization, and even some user space assumption. Again, our goal is not to make Linux perfect, is to understand what would make it predictable enough for a safety use. In short, we are defining the boundaries of what can be trusted, what must be constrained, and what needs to evolve. With that foundation, let's look inside the engine, how VMA are actually created, managed, and sometimes accidentally broken. New section, new picture story. On the conveyor belt, those colored boxes are our VMAs. Each one a small, unique region of the virtual memory, some old code, some data, some just space waiting to be used. Along the side, the robotic arms labeled fork, execd, mmap, unmap, which are the workers, system codes that create, destroy, and reshapes those areas. Most of the time, they work in perfect sync. But sometimes, two arms grab the same box, and that's when race or inconsistencies may appear. In this section, we look at how this production line runs, how VMAs are born, evolve, and can be monitored. Not in a deep kernel archaeology style, but just enough to see why guaranteed determinism later is so tricky. So let's begin with the first stage of the process. What happens when a new application comes to life? Let's zoom out the full landscape of where VMA operates in. User VMA describe each process private memory, code, heap, stack, and shared library. A clean and isolated layout. Above that, we have the kernel virtual address space that, unlike the user space, it is global. Every process sees the exact same kernel mapping. So the kernel always has an immediate access to its own data. The kernel space split into several regions. One is the linear map, a direct one-to-one view of all the physical RAM, fast and predictable. Then we have VMalloc area, a flexible non-contiguous map for VMalloc and IO remaps. A VMem map metadata for every physical page. For the one who knows, here you find the struct page array. And then we have the fixed map, a small fixed address slot for early boot and special CPU structure. On some architecture, parts of the IOs are still appear through the linear map, but modern kernel restricts the raw access for a reason, I would say. And /dev/mem is heavily limited. Normally, device registers are mapped safely via IO remap inside the VMalloc area. The key point here is that the entire kernel layout is constructed during the boot, stored into the init mm, and every process inherits it. So when we say VMA govern both user space and kernel space, this is the picture. One unified virtual space model describes everything the CPU can reach. It's elegant, efficient, and later we say why that same unity becomes a safety challenge. Now, what we see now is the full layout. Let's look at how the process actually gets its own map. Linux has two main paths for this. One copies, one replace. The fork or clone clones the memory descriptor, the struct, and all its areas. Physical pages aren't duplicated. Parent and child share the same through copy on write mechanism. They read the same data, and only when a write does the kernel create a private copy. It is efficient, which is why fork is so cheap. Then we have the execve that does the opposite. It throws the old layout and builds a new one. Text, data, and stack. Shared mapping only survive if to an execve if they are intended to be the sum. That's why the oclo exec exists, to prevent accidental persistence and keep things deterministic. So every process is born into step. Fork clones the address space, execve replaces it with the program we actually want to execute. The only exception is init, created directly by the kernel, but even it ends up in exec during the early boot. And talk of all this, the kernel half of the address space never change. Every process inherits the same mapping. Next, we look on this map, how this map evolving, allocating, freeing, and reshaping it on the fly. We've seen how VMAs get created. Now let's look at how running process reshape it. At runtime, a process constantly adjusts its memory. It uses syscall-like mmap that adds new region, munmap that removes them, brk and sbrk that resides deep, mproduct that change the permission, and mremap that resides or relocated this mapping. This flexibility is one of the Linux strengths, but it also where determinism start to sleep. An mmap that succeed today may fail under memory pressure tomorrow, for example. Mproduct can race with another thread. And mmap can shift the layout in ways that affect timing or caching. For safety, we do have tools like mlock or munlock, which pinch pages in RAM and avoid swapping delays, but they require privilege and are limited by a system-wide locked memory budget. So, dynamic memory is powerful, but inherently unpredictable. Safety-critical system avoid surprise, they pre-allocate, lock what matters, and verify everything as startup. And with that, we close the VMA lifecycle creation, modification, and removal. And we look at how to observe this mapping while the memory and the process are running. So we have seen VMA are created and managed. Before moving on, let's see how we can actually observe them. Linux gives us two tools, proc PID maps, the basic one, and the proc PID smap, the annotated version that permit to see also the shared area. For deeper debugging, the kernel has also its own sensors. Like the best known is the KSAN, the kernel address sanitizer. It uses shadow memory to track which bytes are valid and yells when you step out of bounds or use a free memory. It is brilliant for development, but it is not built for runtime safety. Shadow memory doesn't cover everything. VMAlock modules and other region falls back to a dummy shadow page that silently allows everything. So our detective can miss half of the crime scene. Then we have the LiDAR using K-fence. Instead of instrumenting everything, it occasionally inserts some real gut page between allocation and watches for threats. K-fence is production friendly, but it samples only a tiny fraction of the memory, which is great for catching pattern, not for providing safety. And we also have a glimpse of the future, because ARM64 hardware attacking lets KSAN to run with far less overhead and bring this style of visibility closer to what we might expect in production. KSAN and K-fence are fantastic at catching bugs. They make invisible visible. The issue is not that they failed, it's that they detect after corruption, not deterministically, and mostly not in production. For a functional safety, we need the same kind of visibility, but guarantee and always active. Picture a forest with a ranger on patrol in the mountains. The trail ahead is steep and winding, the kind that eats up hours. Then he spot a tunnel cutting straight through the rock, wide, flat, and perfectly lit. He smiles and takes it. Of course he does. It is faster, simple, and easier. But as we know, there is no such thing as free lunch. That tunnel is what Linux built, the linear map. Instead of climbing the complex path of scattered mapping, the kernel went straight through, one contiguous view of all the physical memory. It worked beautifully, fast, elegant, and without the doors. Every address is instantly reachable, but once you are in the tunnel, everything connects. The same simplicity that makes travel smooth also erases the natural bonds that once kept things apart. That the core of the linear mapping problem, a design made for speed and convenience, now colliding with safety needs for isolation. So let's step into the tunnel, lights on, eye open, and see what expects us on the other side. Let's take a quick step back at the 32-bit days. A 32-bit CPU only had 4 gigabytes of virtual address space shared between process and kernel. At the time, that felt huge. Linux was born on machines that barely dreamed of a few megabytes, and people still quoted the famous 640K should be enough for anyone. Linux split that space, typically 3 gigabytes for user and 1 for kernel, selectable using a config time item. Inside the kernel, the portion lived the linear map, but only for the RAM that could feed it. As a system view, physical memory outgrew that slides. The result was low mem mapped and high mem not mapped. This wasn't designed as a safety feature. It was a workaround to resolve a problem, but it created a nice side effect, containment. The kernel couldn't see all the RAM at once. Accessing IMEM required an explicit temporal mapping. That friction acted like a soft barrier, limiting how far bug could propagate. It wasn't a real isolation, but it was a boundary, an accidental safety net born from an hardware limits. And all this vanished on 64-bit system, where virtual space became effectively infinity. And the wall came down. As said, when Linux moved to 64-bit, it felt like a liberation. Suddenly, the address space was enormous, practically infinite. You could map terabytes of RAM without even thinking about it. So the kernel did the sensible thing. Stop juggling with low mem and high mem and simply mapped everything. No more temporary mapping, no more gymnastic. Clean, simple, and fast. But it came at an invisible price. That accidental safety wall we had on 32-bit system disappeared. Now the kernel can see every byte of the physical memory, including page owned by the user space. It doesn't mean it will touch them, but it can. And for safety perspective, can is already a problem. This is what we call accidental unification of the memory, a convenience that quietly turned a disabling zone into one shared landscape. On the next slide, we'll see why this landscape is more than just a theory, how physical adjacency can make isolation vanish in practice. Here we are. The linear maps stop being a neat architectural idea and start being a real-world hazard. The linear map isn't quite a back alley in the memory. It is the highway where everything runs. Every kmalloc, every task structure, every driver buffer lives here. Fast, efficient, and absolutely central to performance. But this also means that kernel data sit physically side by side to user page. No gaps, no guardrail, just adjacency. So imagine a driver that writes 1 byte past the end of the buffer, one tiny WOF one, and that byte may land in another kernel object or in a user space. No fault, no panic, just silent corruption. The kernel didn't do anything malicious. It simply lives in a world where everything is reachable. For performance, this is a genius. For safety, it is like removing the guardrail just because the roads look straight. That's the essence of the adjacency failure. Not that the kernel misbehaves, but that it works in a space where one brown pointer can cross domain. On this diagram, the green pages are the kernel object. The yellow one are the user pages. They sit one by side in physical memory. When everything behaves, that's just fine. But if a driver overruns a buffer or a pointer goes one step too far, that write can simply keep going right into the user memory. Not malicious, just physics. The address exists, so the CPU obeys. From the safety standpoint, that's catastrophic. Functional safety relies on strict provable isolation. One domain must not affect another, ever. The linear map erases that line completely. This is the entire system safety now depends by one just simple assumption that the kernel never misbehaves. So, what can we do about all this? On 64-bit, everything lives on a vast contiguous address memory. It's elegant and fast, but it also erases the natural boundary between kernel and user memory. Funny thing is that Linux once had such barrier back in 32-bit days. We used that to divide memory into low mem and high mem, not for safety, but because CPU simply couldn't address all at once. That accidental constraint gave us something valuable, part of the memory that couldn't be reached directly. Maybe it's time to revisit that idea, not as a limit, but as a design principle. Imagine, for a safety critical process, its pages are kept out of the kernel linear map. The kernel could still reach them, but only through a deliberate controlled mapping, the way it once did with IMEM. That's the core of this proposal. Treat certain memory as high, not physically, but conceptually. Now, let's look at something that already exists, a real example of what selective isolation could look like. Secret mem FD. It lets a process to allocate memory that the kernel cannot see through linear map. The page are real physical memory, but they are not mapping into the kernel usual virtual address space. From safety perspective, this is fascinating. It proves that physical memory isolation is technically possible without redesigning whole architecture. But, of course, there's a catch. The kernel can see the secret mem FD was not built for safety, but for security. And isolation rules are very strict. The kernel can simply read or write these pages, and even common helpers like copy to user or copy from user often fail or behave inconsistently, especially when the caller is outside the owning process context. And the exact behavior is also depending on the architecture. So any kernel driver expecting to move data into this buffer can break. In practice, only the owning process can safely access this memory. So why it provides or it proves that unmapped memory is possible, and that's conceptually important, it is not yet something that we can use transparent as a mechanism for safety. But it is a proof of concept. Linux can allocate memory that also the kernel must treat as hands-off. And that idea could be the foundation for a future safe VMA. For now, it's more an inspiration than a solution, a reminder that real isolation isn't theoretical. The building blocks are already there. Welcome to the Linux Fortress. It's been standing for decades under constant siege from bug, explore, and very creative community of attackers. Inside the Defender, kernel developers who build layer upon layer of protection, list poisoning, randomized free list, hardened user copies, address sanitizer, and much more. These brilliant defenses are clever, fast, and battle-tested, but they are built for security and debugging, not for functional safety. Their mission is to stop intrusion or fail cleanly, not to guarantee deterministic behavior under stress. In other words, these guards are elite soldiers, but they are fighting the wrong war. They defend against attacker, not accident. Some of these tools still help us. They detect corruption, exposing tiny issues, and make fault visible, but none were designed for guarantee containment or predictable recovery. So in the next few slides, we walk through this Defender one by one to see what protection they really give us and if they fall short through the safety lens. Let's look at the first line of defenders, one that keeps the kernel from quietly self-destructing when memory gets corrupting. First, list poisoning. Linked lists are everywhere on Linux, and if a pointer goes bad, chaos will follow. So the kernel adds integrity check and poison is free pointers. If something touches that memory again, it blows up immediately, not hours later. It is a prevention, but it is not a prevention. But at least it is an early warning system. Then we have free list randomization. This mixed up allocation order in the slap allocator, making it possible for attacker to predict addresses. Fantastic for security, terrible for determinism. Every run looks a little bit different, which makes timing analysis harder for safety system. And finally, we have KSAN, the kernel address sanitizer. It shows memory and catches out of band varieties or user after free. It's brilliant for debugging, too heavy to run in a real system. It helps us to find the dragon, but it doesn't slide them. So these are excellent guards, vigilant, clever, and noisy when something goes wrong, but they don't give us any guarantees. Now, we look at the same other, Now let's look at the other side of the defense, not against corruption, but against running out of memory. When the system is out of RAM, the kernel has one simple mission: stay alive. That's where the OOM killer steps in. He scans every process, scores them, and picks one to sacrifice. It is pragmatic, efficient, and very Linux, but also completely non-deterministic. What lives today might not survive tomorrow, and even if a few knobs exist to drive these choices, it still remains non-deterministic. Then we have the overcommit policies. By default, Linux assumes programs won't actually use all the memory they ask for, a bit like airlines selling more tickets than seats. It is great for utilization, terrible for predictability. You can set strict mode if you like, the never overcommit, but then a simple operation like fork may fail at a time. Finally, we have PSI and Daemon, modern monitoring tools, they measure memory pressure, detect stall, and reclaim pages before disaster hits. Smart, adaptive, and still purely heuristic. Together, this machine are all about availability, not certainty. They keep system responsive, but they don't promise repeatable behavior. And in safety, this is a problem because survive unpredictable is still unpredictable. Let's look at the corner of Linux where performance and chaos shake hands, the VMA cache. The VMA cache is a speed trick. Instead of searching through the entire list of VMA, the kernel keeps a quick pointer to the ones that touched recently. Great for performance until you get a bad timing. If two-thread update mapping are just at the wrong moment, the cache may go stale or even point to a free memory. It isn't theoretical. We've seen real bug where an overflow or stale entirely caused the kernel to walk invalid memory and crash instantly. Then we have the classic example, the dirty code. One small raise in the copy on write logic, and suddenly a process could write a read-only page. Those issues weren't malicious at first, just legal operation colliding at the wrong time. That's why this matters for safety. You don't need an attacker, only concurrency and bad luck. And that randomness is one thing the deterministic system cannot afford. Now, let's look at the map. Not a kernel diagram this time, a proper adventure map. Somewhere on it lies the functional safety, our version of the Holy Grail. And as Professor John once said to his student back at Barnett College, we do not follow maps to bury a treasure, and X never ever marks the stop. Of course, no longer after saying that he ends up in a dusty library pulling up floors, right where a giant X did mark the stop, the spot. That's engineering for you. We make bold statement and then reality smile and say, really? Let's test that. This map is the same. We think we know the route, but the ground keeps shifting. Some paths are smooth, other hide rabbits, swamp, and occasional desert. What matters isn't finding the perfect X, is to understanding the terrain, the architecture, so we can cross it safely. So in the next leg of this expedition, we will do just that. First, identify the architectural gap that makes that journey dangerous. Then outline the safety requirement that define where we are heading. And finally, explore the possible route, the mitigation that might get us there alive. And who knows, maybe this time X will mark the spot. Up to now, we have seen that the kernel already does to defend itself. Things like list poisoning, randomizing free list, catching user after free bugs. All of these are good, but all of that are built for a different battle. These are security mechanisms. They wait for something to go wrong and then try to stop exploit for winning. They assume the architecture itself is sound. The linear map is the opposite. It is not an exploit, it is a design choice. It quietly puts every physical page, user, and kernel alike into the same reach. There is no attacker required. A perfectly honest bug is more than enough. That's the real gap. The system can guarantee the isolation functionally safety demands. Not because a missing patch, but because the foundation itself doesn't separate what must stay apart. And that's why in the next slide, I'll talk about mitigation, not as new defenses, but as architectural changes. So we also talk about what Linux has and what it lacks. In this slide is about safety, what safety actually requires. So how do we close the gap? First rule, isolation, both spatial and temporal. A safety VMA has clear border and stay valid until the end of its lifetime. It doesn't leak into the neighbor, it doesn't outlive its owner, and the kernel itself can't accidentally step in. The second is determinism, as a safety critical process can rely on best effort memory. It must know that memory will always be there when needed. That's where strict overcommit or even the allocation of user become part of the potential safety kit. And third, concurrency integrity. We have seen what happened when race sneak in. They take out that even a single bright permission glitch can undo isolation completely. In a safety world, this is not just a bug, it is a system-level hazard. In short, safety doesn't mean no bugs, it means no surprise. The VMA have to behave as specified every time, no matter what the rest of the system is doing. By now, it's clear the linear map gave us speed, but flattened out the boundaries. So how do we bring some separation back? One direction is layered isolation, modern rethink of what HiMem once gave us by accident. Not nostalgia, but a principle, memory that is not permanently mapped, so the kernel must access it deliberately. If you can see a page, you can accidentally corrupt it. Another avenue is controlled access pool. Secret memfd already show that memory can be intentionally kept out the direct map, but it is an opt-in and is too narrow for safety. Scaled up, this idea become some VMA simply aren't visible at the generic kernel unless explicitly permitted. Then there is the allocation on usage. Today, Linux overcommit, promise first, fail later. How you fix that? Pages committed up front when VMA is created, not lazily at the first use. It trade a little bit of flexibility for predictability, a small shift with a big payoff in determinism. Together, these are not radical rewrite. They are ways of restoring intentionality, making access explicit again. Sometimes safety isn't about adding machinery, it is about putting back the right kind of friction. So we explored what wrong and what it matters. Now comes the part every engineer eventually reaches, turning this understanding into action. First, we need to study how the kernel actually allocated memory. Slab per CPU cache, the fast path are fantastic for performance, but must check whether any of them quietly break under isolation assumption safety relies on. Next, documentation versus reality. Linux moves fast. The docs are good, but the code evolves faster. And you can still find comments describe behaviors that vanished decades ago. Not a fault, just a reminder. If we want to prove safety, we have to verify what's true now, not what was true back in version 0.99. Finally, synthesis. Everything we discussed, the VMI, the VMA lifecycle, the overcommit behavior, linear map, allocator shortcut, fits a concrete safety roadmap, not a rewrite, but a stage measurable plan. What to test, what to change, and how to show that risk is actually going down. And here we are, the last stop of our journey. We talked through kernel, map, races, and even a few dragons. But this story was never about one person chasing a bug or a treasure. It is about a team, the ELISA Linux feature for safety critical system working group, the people standing behind that little penguin on the table, different backgrounds, different perspective, sometimes even different opinion, but all working toward one goal, making Linux a place where safety and open source truly coexist. What you see today isn't just my work. It is our teamwork. It's been shared, reviewed, challenged, and occasionally debated over long calls, and that's what makes it really solid. Because in the end, safety it isn't a solo effort. It is collaboration done carefully. So those all will leave us. We have seen that Linux strength, the linear map, is also the weakest point for safety. Security, hardening catch bug, but can guarantee deterministic behavior. If we want real safety, we need isolation that is deliberate, not allocation that is predictable. So what's come next? Define what safe DMA actually means, testing a way to isolate it, align this work with the ELISA architecture team so we can build into a coherent roadmap. And this is not the end of the discussion, it's the end of the design, is the start of the design. Oops. And for all this that keep their vegetable so far, this is the moment. You can throw if you want. That's it. And by the way, if there is any question, I'm here to answer.
There is actually one in the chat saying, is the 32-bit legacy mapping still followed by the supported 32-bit architectures, e.g. ARM, v7, Spark 32, and so on? Do you know?
And let me look at it. So how I access the chat in this thing of sharing. Let me see the chat.
Yes, I think it's one that.
Yes, it is. In the all the 32-bit system still support the IMEM. But please consider that the IMEM is not meant for safety. It is something we can reuse for safety, but it's not meant for safety because you can have a VMA that is composed by high mem and low mem. The kernel doesn't pay a lot of attention on what put in a newly allocated memory. It just use what it have. The idea would combine all the things that I propose in the talk. So the allocation of use allows to make the allocation at one time, and this would allow to move all the memory decision in one place. So you can have, when you allocate on usage, you can decide to use a restricted pool of memory that can be removed by the linear map the same way that secret memfd does currently, and have a VMA that is composed only by memory that is not linearly mapped into the kernel linear map area. In that way, you are reasonably sure that the kernel cannot corrupt that by chance. It can still corrupt it, but it must access before corrupting. It needs different dynamics. Anything else? In the presentation sharing in the event, I will follow the slide.
It's definitely a way secondary order issue. But one of the things we saw at the workshop last year with NASA is some of the implications of radiation onto memory systems.
Mhm.
Are there any good mechanisms out there for detecting corruption that can be applied to the kernel in some of these isolated areas?
But it is different because, for example, if radiation corrupt memory, you may have something like error correction memory that can detect. But if the kernel corrupts because an overflow.
Oh, I know. Yeah, I know. I'm just wondering, is these mechanisms, how might they end up interacting?
Well, I think yes.
Okay.
So one of the things we are, I see moving in the kernel community is a pool of memory where you have systems that have different kind of memory. For example, so far I know that server has error correction memory and laptop has not.
Right.
But recently there are systems that has a small pool of error correct memory and normal memory, and you may want to use the error correction memory only in a few cases, so you need a pool. I know that something is moving in that area.
So, I mean, when it comes to hardware failures.
Yeah.
You can't, I mean, so what Alessandro is mentioning is, like if you have a system on chip that allows to have different pool of memory where one is diagnosed
Correct.
versus another one that is not, you can implement in the kernel a mechanism to, to pull memory from either pools, but it is not possible, to have a diagnostic memory mechanism of memory corruption in the kernel unless you effectively implement a march test in the. So effectively, what happens in reality is that either you have like an integrity field that is associated, with the with the memory cells, but that is checked, when the memory is read, or you have like periodic march tests that are very, very, time consuming. So you need to take the system down periodically and, run the march test. So you write it back and verify, that
When the prices.
exact. So, and this is for march tests are for permanent. When it comes, to the transient is.
Yeah, but usually what you do have to detect these kind of radiation errors is something like a parity bit or check bit, and then you just run it in the background and you detect there is some random corruption. But this is not what the.
No, I'm just thinking though that in some situations, some of these things may interact, and what happens when you're working in an environment where this is potentially possible, and you've got these mechanisms going, and the allocations. How the allocations are working with them.
So,
and that's what I was just trying to figure out in my head.
What you usually do is when you do the design of a safety system, the software developers believe
Have to do the specific.
that the hardware is perfect.
Yeah.
And what they do is they just implement the support for the diagnostic measure of the hardware. The hardware guys that do all the FMEDA, the fault injection analysis to verify that that diagnostic mechanism have reached the coverage target required for that seal or ASIC. So this is basically first the hardware guy does this analysis, they define the safety mechanism, then they say we're done. Then they document all of this in the hardware programming manual, the safety manual of the hardware, they pass the pull to the software guys.
It then says
and they ask them, please, implement the kernel in the firmware or whatever, the support for this software test library or, you
Right.
know, diagnostic driver that react to, you know, these interrupt that are triggered, you know, when there is a parity bit that is not,
Mhm.
so usually this is the way.
Different, yeah, different mechanisms, but the different architecture, that's okay.
Any other?
So when we were talking about this high enrollment and that the kernel does not see the user space and that things, I'm wondering, does this have impact on things like file I/O or network I/O performance? Because now the data, like the kernel cannot easily copy the data into the user
May
space.
have.
And
This was one of the problem that once 32-bit had. And the reason why now 64-bit doesn't do this anymore.
okay.
Once, because you have normally the kernel memory, the virtual address space is divided into blocks. 3 gigs for user space and 1 for the kernel. So the linear map exists inside the kernel and is not all the memory allocated by the kernel. So the linear mapping in 32-bit with this separation is usually 800 megabytes. Everything that is after this 800 megabytes cannot be linearly mapped by the kernel and needs to be a VMA, a high mem. And so temporally mapped, used, and unmapped. This was a problem because when Linux started, 4 gigs was enormous and all the physical memory reached into this 800 megabytes. But then things changed and you also had that thing like pi, for example, in Intel 32-bit, where address space reaches 36-bit, which means that your virtual address space never could reach all this memory, and you always will need to map this high memory in some way. By the way, there is an equivalent also for ARM v7 of this pi. I just don't remember how does it call, but it is the same also for ARM.
But I guess since you said that, like you're saying for existing architectures like ARM v7, they still use this technique. I guess the kernel as a whole is still able to manage this kind of approach.
Yes, but the code is simply not used in 64-bit.
Yeah.
It's not even compiled in the kernel because it doesn't need. And if you remove the safety use case, it doesn't need to use it. Why wasting time in doing something that is not useful? So this could be a use case for reintroducing this code in 64-bit for a different use case. But in order to do this, whoever will do this needs to find the use case and prepare all the things because it doesn't, reintroducing the mechanism is not enough. You need to introduce other mechanisms to make it use at the right time.
And by this, we close the session.
Okay.
And one more point over here.
Yeah.
So the high mem support is supposed to be removed by 2027.
Sorry?
The high mem support for 32-bit architecture.
Mhm.
That is supposed to be removed by 2027.
Oh, great.
That's
what
So 2027 is supposed to be the deadline. So that is still ongoing.
So it's planned to remove all the support for 32 bits.
32-bit support will be completely removed by, he said, like in next 10 years. But
Yeah,
that's
yeah,
still-
there was a very good talk at Lenaro Connect on that from Art.
Okay.
And that should be online somewhere.
Yeah, so you can see that this last year's, this year, so it says Aaron gave that talk about 32-bit architecture removal and most.
Great.
Stop the recording?
Yeah, just don't call it high, man.